All right. So feel free to kind of follow along. I think this notebook was posted last night. But in general, just make sure that you have, before you start, you've installed all of these required libraries before you try to run the notebook. But I'll kind of go through this. So basically, we can import these libraries. So you'll see here that I have GSEA Pi and Blitz GSEA. And then also importing that stats, SciPy stats library for the Fisher exact test. And essentially, the example data that we're going to use is actually the example data from the Blitz GSEA GitHub repository. So you can see the actual data here on GitHub. But essentially, we're just looking at this pre-computed signature that's comparing, that basically represents the differentially expressed genes between old and young muscle tissue samples from the GTEx dataset. And then in the case of this code notebook, I'm mainly looking at the KEGG 2016 gene set library because that's the gene set library that all of the methods support, or all of these algorithms and packages I'm using support. You could also feel free to sub out KEGG 2016 and try different libraries on your own if you're interested. Also, let me know if the text is too small or anything. I'll try to zoom in a bit more. But essentially, the first one we're going to look at is GSEA Pi. So here's the most recent paper citation. I believe this package was first released in 2017. In this most recent paper, they say that their package and Blitz GSEA are the only Python implementations of GSEA. If you find another one, feel free to Slack it. But this tool has been around for a while, and it's pretty fast now. But with the GSEA package, there's a lot of different functions that are available. But for this example, we're just going to use their pre-rank method, which you can find on their documentation. And this is just because we already have a computed signature. If you have just expression data, you're starting with just expression data, they do have a function where they can take that gene expression data, compute the signature, and then perform enrichment analysis all in one step. But in this case, we already have a signature, so we're going to use pre-rank. And in general, you really need to concern yourself with two required inputs. So this RNK or rank parameter, which is just going to be your signature data. I believe this can be a pandas data frame or series. You can also use a file name, I believe, but double check the documentation. And then you also want to give it the name of the gene set that you're looking at. And the nice thing about this package is that it does support almost all of the enricher gene sets. So here we just give it this KEGG 2016 name. And then I set outdoor to none because I don't want us to save the results anywhere. But if you want to say the results, you can give it this an argument here. And so, oh, I did not run this one. So first we're going to pull the data in, and then we're going to run this. I think it'll take a little bit of time. We'll see. All right. Okay, so now it's done running. And then what we can do is we can actually look at the results using this 2D results object. So here we can see the ranked terms from the KEGG 2016 library for our input signature. And then we can see the overall enrichment score, the normalized enrichment score, the p-value, the adjusted false discovery rate, or the Q value. There's also this family-wise error p-value, and then these two values just represent the percent of genes in the term gene set that are basically ranked before the peak of the enrichment score, and then the percent of the genes in the input gene set that are ranked before the peak of the enrichment score. And then these are those genes that are represented here. So mostly we're concerned with these enrichment scores and the ranking of the terms. So you can kind of see that here we have the systemic lupus, erythematosus term, Staphylococcus aureus infection. We have cell adhesion molecules. And you can kind of keep these terms in mind as we go down through the notebook. So now we have this ranking, and maybe you only need the ranking because you're only really interested in the terms themselves. But if you want to see that running sum plot that they generate for each term, you can use this GSEA plot function that they offer. And in this case, basically, the short way to call this is that you want to give it the ranking once again. And here, instead of using the original signature data that we have, you can just directly call the ranking object from your GSEA Pi results here, just for continuity's sake. And then you also want to give it the term that you're interested in. So here, I'm actually going to look at the cell adhesion molecules term, because maybe I'm really interested in how this term relates to my input genes. And I'm calling that by basically just calling the second value in the term column from this result table. And then this line might be a bit confusing, but what this does is that there's a lot of other arguments that this function requires, but they are all arguments that are in this results table. So if you just use this term, you're basically kind of giving those arguments all in order. If you have more questions about this, you can look up this double asterisk notation in function. But this should provide our plot, and you can see that now we have this nice running sum random walk plot, like the examples I've shown. And you can see that indeed there seems to be a bias towards the genes at the front of the graph, which is why you see this nice positive supremum and this nice curve going down. So this is a quick way to generate a plot. So now moving on to the Blitz GSEA algorithm. So Alex, correct me if I'm wrong, but I believe this is an alternative implementation of the pre-rank algorithm from GSEA Pi that's faster, right?
Yeah, that's right.
Yes, so you can read the original paper if for all the students who are interested. But Blitz GSEA similarly supports comparison against enricher libraries. You do have to actually extract the library that you want by using this get library function. So once there, we've set Blitz live to this KEGG 2016 library, and then we can call this GSEA function on our signature as before. I believe you do have to reset the index in order to run this, and then you just set library to Blitz library. So it's pretty straightforward, and I think there'll be a nice progress bar. Yeah, also, if anyone is following along and you have any issues, just let me know. I think I can see hands or chat, or just unmute yourself. Let's see. Okay, there we go. And then so now, once again, we can use we can view the results. So actually Blitz result just returns a data frame. So you can just directly view, or Blitz GSEA returns a data frame as a result. So you can just directly view the results as a data frame. So once again, you can see here the terms, the enrichment scores, the normalized enrichment score, p-value, and then the other different columns. Notice that we have basically the same terms as the GSEA Pi result, but because the algorithm is slightly different, the first three are in a different order. So you'll see now that cell adhesion molecules is actually ranked first, and then the other two are ranked below. So you can also plot a nice little publication ready figure using this plot top table method. So I believe this will work. I think one thing about this is that I did have to rename you do have to rename the columns to be their integer forms instead of the string forms. But if you just give it basically your original signature data, you give it the library that you want, and then you give it the results, and then also the number of actual terms that you want to see. You get this nice image. And the benefits of the image is that if you're writing a paper, you can actually directly just put this into your paper and it looks quite nice. Also, of course, this Blitz GSEA package also offers the option to create this running sum plot. So here, once again, you want to give it this your original signature data. Yes, Tori?
If you scroll up and instead of giving it you have like n equals 15, like can you set it based off like p-value? Like could you be like, I want to see all the or like all the, I guess, pathways or gene sets that are less than like 0.05?
Yeah, that's not an option right now. So I think the only way you could do it is by just counting in the table how many and then passing them. Yeah.
Okay, thank you.
It's also like if you get too many, then it's kind of hard to display, I guess, because you can get quite a few significant pathways, but.
All right. Yeah, so going back to this plot, so here, you give it your signature data. You can say which term you actually want to draw the plot for. And then once again, you give the library the result. I'm doing this compact equals false because I want this full plot. And let's run it. And then you'll see this is what you get. If you choose a different term, just to prove that this is a live demo, you'll see once again, you can get this plot. And then if you change compact equals true, you get this slightly shorter plot where the bottom part is kind of condensed. But yeah, feel free to explore with the different gene sets for both of those previous packages as I move on. So this third part is actually going to go over how you would compute Fisher's exact test using the SciPy stats library. If you have a 2x2 contingency table, generally this will mean that you're going to have to do a little bit of processing of your data to actually even get this, to build this original table. So I'll show a faster way of doing Fisher's exact test if you really want to later. But if you're interested, this is basically how you would actually generate the table. So first, you have to get your gene sets. So usually the cutoff that we tend to use is around 250. There's no hard rule for this, but generally you want enough genes that you're capturing enough information, but also not so many that you're just basically putting the entire list of all the genes into your gene set. So here for the up and the down genes, we're just sorting our original signature by those expression values, and we're just going to get the top 250 when the list is in descending order as our up genes, and then in ascending order, the top 250 will be our downregulated genes. And these will be our gene sets that we're looking at. And for the rest of this notebook, I really only use the up genes. I left the down genes for you guys if you want to try to do it by yourself later on. But in general, for Fisher's exact test, you also can only look at a single gene set at a time. So you saw in the other two previous packages, you could get results for the whole library at once and then just look at individual gene sets. But here we actually do need to extract the specific gene set that we want in order to build that contingency table. So luckily, we can actually do that from the Enricher API. So if you are lost at this part, you can read the Enricher API documentation on the Enricher website to see basically how this works. But essentially, this is the code that you would use to actually get this specific gene set. So we're looking at the same cell adhesion molecules gene set from the KEGG 2016 library. And let me actually run this code before I forget. So here we can see that we've gotten this gene set and there's 142 genes in this gene set. Okay, this table is messed up. but this is basically what you're looking at. So you're looking at your genes that are upregulated and your genes that are not upregulated. And then also you're looking at which genes are in this gene set and also which genes are not in this gene set. And what this means is you're going to have to do a couple set operations in order to get this, because when you want the genes that are both upregulated and in the gene set, so you're looking at the intersection between your up genes and also this enricher gene set. But for the genes that are not upregulated, so note that this is not just the downregulated genes. These are any genes that are not in the upregulated gene set. So don't just put down genes here. You actually want to take the difference of the original, all the genes in the signature, and then take the difference from the up gene set, so that you're not excluding any genes. And then you're going to intersect that with the enricher gene set. For upregulated genes that are not in the gene set, so once again, you can just take your up genes and then take the difference with the enricher gene set. And then finally, you're not upregulated and also not in the gene set genes. You want to take all the genes that are in your signature and remove the upregulated genes, and then also remove any of those gene set genes. I think that might have been a bit confusing, but I think I explained that correctly. If anyone has any questions or needs clarification on that part, let me know. Okay. And then, so basically what we can do is you can use NumPy array function to basically create this little table as an array. So you'll just take the length of each of these intersections and differences that you just created. And note that this is why you can use an unranked gene list with Fisher's exact test, because you really only care about the number of genes that are in each of these categories. You don't actually need to rank those genes. So let me make sure I run this code block. All right, and I think actually if we want to just see our array, so you can see this is basically what our table looks like. And then you can actually compute the Fisher results, by calling this SciPy stats Fisher exact test function. And you'll basically just give it this table that you just created, so this up array. And then here we're just interested in the one-sided hypothesis test, so you can just give greater. I think the other options are less or two-sided. And then what you can do is you can print the p-value that you get from these Fisher exact tests. So note that this actually does just give you the p-value, not just the probability. It does give you the significance. If you're interested, I think insert sample. You also see that what it gives you is basically, this would be the actual statistic, and this is the p-value. I have to look into why that statistic is like that. But that is basically the longhand way, I guess, to compute Fisher's exact test for a specific gene set and a specific input gene list. But as I said earlier, many times, Enricher uses the Fisher's exact test, so you can actually just use the Enricher API to compute the full enrichment analysis results using Fisher's exact test, and this will actually just compute the results for all of the libraries and gene sets in Enricher. So instead of doing it one by one, you just get all the results at once. So once again, to avoid going too deep into API calls, you can just look at the Enricher API documentation. If you have questions later, feel free to ask in the Slack, or if you're looking at now, feel free to ask now. But essentially what you do is you want to upload your gene list to Enricher using this add list endpoint. So we're just going to upload the up genes once again. Note that Enricher does require these to be submitted as a new line separated string, so you can't just pass it up genes to list. You do have to turn it into a new line separated string. And then you can name your gene set. So here's just up genes from the GTEx aging muscle signature. And then you make your API call, and you should get some kind of this object, so with some kind of short ID and then a user list ID. And then you'll want to save these and remember them for the rest of this notebook, because what you can actually do is you can view the results for this specific list in Enricher on the web app by just plugging in your short ID into this URL. So I think this is technically the previous code cell I ran. Note that even if you submit the exact same gene set, it will give you a different short ID. So let me just copy this over. Then if we click this, we'll see, we can see that we have our genes here, 250 genes. We can see our gene list. And let's see, if we go to legacy, we can see, where's KEGG 2016? Did I miss it? Here it is. Here we can see our KEGG 2016 results. Yeah, so note once again that these results are different, are more different from the two GSEA results, just because now you're not looking at a ranked list, you're just looking at a set of genes, and also it's a totally different method, Fisher's exact test versus the GSEA Kolmogorov-Smirnov test. So you'll see that some of like this term, I believe, showed up in the previous results, but a lot of the other terms are different from the results that you would get from GSEA. So that's also something to keep in mind, that the method you choose, make sure you understand what you're choosing, because the results will differ. Yeah. But so that's nice. And now you can see all of the results for all the different libraries that you could possibly be interested in for this specific data. Yeah. And then finally, I'll go over how you can actually just, if you want to keep it all programmatic, like you need the enrichment results for a downstream analysis later on in your code that you're writing. The last part of this code basically tells you how you can actually use the API to also perform enrichment analysis. So instead of going to the web page and clicking through, you can just get all of the results in a data frame. So this, you're going to use this enrich endpoint. Once again, documentation is on the Enricher API help page. And all you're going to give it is basically this user list ID that you obtained earlier. So note that for the URL form, you use the short ID, but for the API, you're going to use this user list ID. And then background type argument, you just give it the library, which is KEGG 2016 that we're interested in. And then we can go ahead and run this. And then what you can get is you can actually turn this into a data frame. And you'll see you get the same results that we saw on the web page, but now you have all of this in a data frame in your code. So now if you're interested in looking at specific terms, or you want to see the overlap between the gene sets, now you can actually go in and access these from this data frame that you have. And I believe that is all. Like I said, okay. As I said, you can play around this notebook, see if you can plot different libraries, different terms, try a different data set. Also, if you're looking for a place to start, since I did this whole analysis with at least for the Fisher's exact test and Enricher section with the up genes, you can try to redo it for the down genes from the signature. You can also try to combine the up and down genes to see what the results look like. But in general, feel free to mess with this notebook and explore some of these methods. And then, as always, Slack if you have any questions or comments.